One of the problem types that we are going to solve in chapter 21 is the computation of the electric field produced by a continuous charge distribution. So in that case, we have some kind of an object, an extended object. It's not a point particle, where the some amount of charge is distributed somehow, uniformly or non-uniformly. It just depends on the problem. And then we are going to choose any point outside, and we would like to compute the electric field in here. Okay, in that case, we have a, in a way, some kind of a expression that looks like a formula, right? This is this expression in here that we usually write down. Unfortunately, this is not a complete formula. This is actually a recipe. Means that it basically contains some kind of instructions for computing the electric field, right? A lot of people do not understand that this is actually a recipe, and they think that this is some kind of an integral that is ready to be evaluated. No, it is not. This is basically the very first stages of how you should actually try to write down the electric field. There's still more work to do, and we are going to concentrate on problems of actually being able to write down this integral expression in here. Okay, it's a recipe. It basically tells you what you should do, right? What it says to us is this. First, it tells you that you have to divide your body into small charges, small pieces. So I'm going to show it like that. So somehow you are going to divide your extended object into small pieces like that. And then you are going to compute the amount of the charge on each piece, and dq somehow represents that charge in here. And basically we need to do an integration at the end. So as a result, this dq should actually indeed be very small. So as a result, at the end, we are going to take the limit where this quantity actually goes to zero. So the volume of, or the, I don't know, the area of each of these pieces should be going to zero at the end, at the integration stage. In any case, so you just choose a piece. So dq somehow symbolically represents the charge of that piece. But now I can think of this as a point particle. So let me choose a different color now. So in that case, I need to draw a line from the charge, that infinitesimal charge, to the point in question. And let's say that r is the distance of that point charge to that point. This might be a variable, usually is. Then there is this r unit vector, which basically is defined by using this orientation in here. And we know that this point charge produces an electric field, which is basically 1 over 4 pi epsilon 0 amount of the point charge, which is dq, divided by r squared times r unit vector. So that's the electric field produced by that point charge only. And at the end, of course, you have to do this for all the charges and then sum over them. And in the case when dq goes to 0, this is actually, the summation is actually is going to be converted into an integral. Okay, so as a result, this thing basically contains some instructions. And so as a result, it is not possible to integrate this yet at this stage. Basically, dq is some kind of a variable that you need to be expressed in terms of some kind of an integrable variable. R is a variable, and r hat is also a variable. And moreover, there's another complicating factor. This is an integral over a vector quantity. So this r hat unit vector in here is a vector. And so therefore, we have a vector in here which might be changing its direction if I choose the charge on at different points. In any case, so as a result, this is a little bit more complicated. So for that reason, you have to be careful with this. So handling the vector part is kind of easy, actually. So instead of integrating the vectors, you basically integrate the Cartesian different components of the vectors, right? So as a result, we have the x component of this r unit vector in here should be entering if I'm computing the x component of the electric field, and I can repeat the same thing for the y component and so on. In any case, how do you divide a given extended charge distribution into small pieces? Well, that depends on the problem. In some cases, it's too complicated. This is basically way ahead of us. This is something that we cannot do in that class. Lots of problems are complicated, but there are some simple problems that we can solve in this class. So as a result, I'm going to give some examples from these. So in each case, how you do this division, how you do that integration, that's going to depend on what the problem is. Okay.